I am presenting Aardvark, Comparative Visualization of Data Analysis Scripts. Debugging in data analysis often looks quite different from traditional debugging. It tends to involve exploratory tasks where there is no right or wrong answer, but varying qualities of results. For example, people may want to assess the quality of their final results, understand how they reach their final result, or examine the analysis under different settings, such as different parameters or analysis algorithms. We're going to focus on this last task of examining the analysis under different settings. This task aligns with a common debugging practice in any type of program, from software engineering to data analysis. The idea is that people tend to run their program, observe the results, make a small change, run the program again to identify the effects of that change. To give you an example, we will examine the workflow of an analyst running an interactive dimension reduction. The way that dimension reduction works is that the analyst directly manipulates a set of points to specify classes in the data that the dimension reduction failed to identify, after which the dimension reduction updates the layout accordingly. After performing a few interactions, our analyst is curious to know how the number of points manipulated per class affects the optimization's progression towards a good quality clustering. In this setting, the edit the analyst performs is manipulating a different number of points per class, and the analyst must run the dimension reduction once per interaction, creating this cycle of edit, observe, or edit, run, observe, and repeat. Using traditional methods, the analyst is limited to inspecting multiple instances of their desired debugging method. For example, they can run a step-through debugger to assess the clustering quality for a given interaction, but to compare across multiple interactions, they must either recall values from the initial run or run two instances of the step-through debugger simultaneously, comparing values at each step while building a mental image of the overall trends. Similarly, with print statements, they must compare side-by-side printouts of values while trying to incrementally build and compare mental images of the two executions. Finally, they can write values out to a file and perform custom analyses or build visualizations to compare the two instances. However, there are two clear problems with these existing methods. First, they require a lot of manual and mental overhead to gather and understand the values. And second, they do not inherently support this comparison across multiple executions to identify the effects of the script edits. In recent work, I introduced a method called Anteater that addressed the first problem by automatically tracing analysis scripts and visualizing the execution structure and desired values. However, Anteater still suffers from the same problem as existing methods, where people must either recall the past visualizations or run two simultaneous instances and compare across them. So while it assists with the first problem of lowering mental and manual overhead, it does not support comparative debugging across multiple instances. So we need a solution that supports comparison while reducing manual overhead. To build such a solution, we must address two research questions. First, how can we identify and capture the differences between two consecutive script executions? And second, how can we apply visualization principles to automatically generate comparative visualizations that illustrate the effects of script edits? In response to these questions, we introduce Aardvark. Aardvark builds from Anteater using the same underlying tracing infrastructure. However, it now automatically identifies the differences between two consecutive executions and generates visualizations to illustrate the effects of those changes on the traced information. To demonstrate Aardvark, we'll walk through our interactive dimension reduction example. First, the analyst arranges one point from each cluster and runs the projection with Aardvark, generating the visualizations on the right. They observed from the scatter plot that as the optimization function converges, the quality of the clustering does not. It fluctuates between good and bad quality clusterings throughout the entire optimization. So the analyst begins to wonder if the optimization is not quite aligning with their clustering task. To investigate this, they then arrange 2 points per class and run the analysis with Aardvark to see how this affects the optimization. In the back end, Aardvark will now perform two distinct diffs to identify the effects of that change. First, it will diff the abstract syntax trees of the two script versions. It then uses this information to build a mapping between the two versions of the script to identify which portions of the original version correspond to which portions of the new version. Aardvark will later use this information in identifying the trace differences. Then, Aardvark actually performs the trace diff, where it identifies the effects of the edit and structures that data for visualization. The way that it does this is that it takes two traces that it captured, the trace of the original script on the left and the trace of the modified script on the right, and it traverses through them to align the two traces and identify corresponding execution nodes, such as function calls and variable assignments. It identifies the nodes that exist in both traces, using the mapping from the first step to verify that two nodes correspond to the same source code. Then it identifies the portions of the trace that differ from one another. It can identify nodes that exist in the original version but not the modified version, shown in red, nodes that exist in the modified version but not the original, shown in blue, and variable instances that exist across both versions but now have differing values. Finally, having identified the differences, it merges the two traces together into a single structure that is then passed on for visualization. Back in the front end, Aardvark takes that combined trace and applies Gleicher et al.'s taxonomy for comparative visualization to automatically create comparative visualizations that illustrate the differences between the two executions. The end result for our example looks like this. We'll take a closer look at each visualization individually. We first present a comparative icicle plot that uses juxtaposition to present both execution structures in an aligned space. The execution of the first script builds down from the central block, while the execution of the modified script builds up. The blocks in the modified version that are highlighted with blue borders indicate nodes that only exist in the modified version. For our example, this means that the optimization with 2 points per cluster took longer to converge than that with 1 point per cluster. The blocks lined with gold indicate variables whose values changed in the modified version. In our example, this makes sense as we would not expect the cluster quality to stay constant across the interactions. Moving to the value visualization, we present a comparative scatter plot using superposition to illustrate the differences in the progression of the clustering quality throughout the optimization. The red points indicate values from the original version, and the blue the modified version. We see that while the clustering quality seems to fluctuate a bit less and tends to stay in a higher range of values, it still never really converges on a good clustering. Again, this suggests that maybe the optimization does not quite match the clustering task. So our analysts will continue to explore, and this time they're going to move 3 points per cluster. Now they see that the clustering quality behaves in a much more structured manner, moving in a progressive way towards the final clustering. However, as the optimization converged, the clustering didn't continually progress towards a better quality clustering or even converge on the best solution. So while this seems to be an improvement because it's more structured, it's still a bit concerning about whether it actually matches our task. So to test this one more time, the analyst is going to perform one final interaction, organizing 4 points per cluster. Now they see that the clustering seems to converge with the optimization. It continually works towards a better clustering as the optimization converges and lands on the best result it has yet achieved. Using Aardvark, the analyst was able to quickly and easily compare their analysis under different settings with minimal manual and mental overhead. In this talk, I presented Aardvark, a method that automatically captures, identifies, and visualizes the differences between consecutive runs of an analysis script. In doing so, it better supports this edit, run, repeat cycle common in exploratory debugging tasks while alleviating the manual burdens of existing debugging practices. So we have a couple of directions for future work. First, being able to compare more than 2 executions. For example, it might have been nice to take a 4-way diff of those 4 different interactions and view the differences all in one space rather than in consecutive pairs. Second, there's opportunity for future work in computational notebooks where a single workflow might contain substantial repetition. Where Aardvark currently supports diffing of 2 workflows, there is opportunity for diffing within a single workflow to identify and visualize repeated analysis behaviors and the different results achieved. With that, I will conclude my talk, and thank you all for listening.